The answer is within living memory. That theory is less than 80 years old. And the confirmation of it is less than 30 years old. But in between, there were two other theories. That the sun was glowing from just sheer gravitic energy of shrinking. It's just so massive that as it slowly shrinks, that's generating the energy at its limit. That gives you a very short lifetime. And then it's due to stuff falling into it. Lots and lots of dust and stuff like that falling into it. That gives a really short life. It's nice that we now have a theory for the sun that explains why the planet has been around for a long time through nuclear fusion. It's even nicer that we can stop having to come up with new theories every 70 or 80 years because we've done the experiments that actually determine that that's the right theory, subject to little tiny corrections and details. Raleigh couldn't do that experiment. He couldn't take a sample, or at that point spectroscopy wasn't really understood to the level where it needed to be. There was no way to tell whether the sun was made out of burning acetylene and oxygen. There was no way to tell that it was due to gravitational contraction. But there was a way to tell that it was due to nuclear fusion. So the fundamental kind of physics that I'm interested in is this question, well, how do you know if that theory is right? How do you know that that's what's actually going on? So my specific topic, I'm going to stop stalling and just move on, is dark matter. So this is an astronomer by the name of Zwicky. And he asked a very fundamental how do you know question. Often these how do you know questions are viewed as obvious. Everybody knows the sun shines via chemical reactions. Everybody knows that the reason those funky things that look like my screensaver, that's a collection of stars and it's swirling around. That has to be. What else could it be? Right? Well, actually it's pixels on a screen. But if you were looking at it in the sky, it's swirling. That's got to be. And so Zwicky said, okay, let's try and figure out if that's correct. And he made measurements, spectroscopic measurements, of how fast stars were coming and going in one of these disks using redshifts and blue shift as a function of how far out they were. Because it's not just that if it's spinning, you expect one side to be going away and the other side to be coming toward you. There's actually a prediction of how fast. The stars that are, they're basically orbiting around the mass of the galaxy as they get farther and farther away, as gravity drops off because you're getting away from the mass of the galaxy. You can work out how much slower they should go. And you get a curve that looks like this. The mass of it, it's not quite the 1 over r squared that you've learned from orbits around the planet, because galaxies aren't spheres. They have central bulges, they have disks, they're sort of funky shaped, but you get something that looks like this. And he made lots and lots and lots and lots of measurements, and finally he published, this is actually from his publication, this plot. I've colorized it, but other than that, it's the picture. This is what he observed. Now, a couple things about this. As new freshmen, you've been in Physics 7A or H7A, you've heard your colleagues ask about significant digits, and maybe your instructor said, don't worry about significant digits, physicists always put error bars on their quantities. What don't you see in this picture? There are no numbers, there are no error bars. There were numbers and error bars in his paper in other places, but here he was actually explaining the problem. The problem is that a very simple model of these galaxies as being made up of stars whose masses we understand and gas that we can sort of see predicts a certain dependence of velocity, and he was seeing one that was flat. And this puzzle was around for a long time. There are a lot of ways you can deal with it. You can pretend it's an error, which is actually often, for scientific mysteries, it's a mistake, it's a good first bet. You could think that maybe over very long distances, not from here to the center of the Earth, not from here to the center of the Sun, not from here to the nearby stars, but over the thousands and thousands and tens of thousands of parsecs around it, or 50s, hundreds of thousands of light years around the center of the galaxy, maybe 1 over r squared isn't quite right. Maybe there's another term that we don't notice for nearby that messes up 1 over r squared. We'll explain this, a little bit stronger far away. You'd like to know, right? A lot of people had theories. You'd like to know. And I'm not going to go quite chronologically. I'm going to go in terms of how you untangle the picture. Here's the next step in this. You need a really good projector in a dark room to be able to see the beauty of this. This is a Hubble Space Telescope picture. Who was Hubble? Who, physically? I mean, why is it named for him? Why is the Hubble Space Telescope named for Hubble? His name was
Finding
Hubble.
the redshift and blue shift of the expanding galaxies, right?
So Hubble was the one who worked out that if you look at galaxies that are farther away, they're receding faster. The farther you look, the faster it's going away. He measured that by a redshift. And this is the argument that the universe as a whole was expanding everywhere. Why was the satellite named after him? Its primary scientific purpose was not to take this picture and a whole bunch of others, but to really confirm and nail down that relationship, make an accurate measurement of how far away these things were, and draw that proportion and establish the parameters, basically called the Hubble parameter, of what that proportionality is, because from that you can work out the age of the universe. And that's what paid for the $1 billion. Dollars were worth more back then. But all sorts of other science was done by this. So just as a small aside, there is a middle school in Wheaton, Illinois that's named for Hubble. When it was turned from a high school, I went to it briefly, but it threw me out. The three famous graduates of this school were Hubble, Red Grange, who none of you have ever heard of, but was a famous football player in the Midwest, and the Belushi brothers. And they had a poll as to who this school would be named after. And essentially everybody in town over the age of 40 voted for Red Grange. And everybody under the age of 40 voted for the Belushi brothers. And there were 3 votes for Hubble. 3, count them, 3 votes for Hubble. This town is 2 towns over from where Fermilab is, and we think that those 3 people were probably refugee physicists. So since neither of the other 2 were acceptable, they named it for Hubble. So he has a telescope and a middle school named for him. In this picture, if you look very carefully, you see an interesting thing, which is a bunch of these little lines. It's hard to see on a projector, but if you get a really high quality image, you can see them all. There's one there, there's one here. And if you sort of defocus your eyes a little bit, you almost get a swirling effect. There's a really nice arc up there that I hope you can see. What are those? Well, if you look at it with a spectroscope, you can convince yourself that they look like galaxies that are receding quickly, so are very far away. This is a false color picture. It's sort of highlighted to make these things easier to see. So they're behind what we're looking at. And if you believe general relativity, and don't forget the theme is, how do you know? If you believe general relativity, you can work out that there must be a bunch of mass in the front. These are not stars, these are galaxies. So this is that's a star, but it happens to coincidentally be here. This is a cluster of galaxies. It's massive. And just like general relativity predicted that light passing the sun would be bent in, it predicts that light passing very long distances around a cluster of galaxies will be bent a tiny amount. But it's very far away, so that little tiny bending results in this smearing. If it was a perfect lens, you get a dot far away becomes a circle as it goes through the thing. It's not a perfect lens, it's sort of lumpy, and so you get these little slots. From them, you can work out the mass that's bending. If you've got enough of them, you can make a good measurement of sort of the average. And what you discover is something that's consistent with what Zwicky was showing you, so went the wrong way, is that the galaxies that he was looking at, this can be explained in terms of mass you can't see out here. That's adding more gravity and therefore making things swirl around faster. If you look at this, you can add up all of the mass you see in these galaxies, in the dust in between them. We had infrared and other measurements of dust and stars and all sorts of stuff, X-ray measurements of hot gas. You find that there's a lot more mass than you can explain. There are lots of theories. One theory would be, well, general relativity is wrong. There's something wrong at large distances. It's exerting more force on the light. It's bending the light more over large distances. Another theory, which actually got some traction, was that a long time ago, because this is very far away, a long time ago, protons were a lot heavier than we thought they were. Lots of theories. You could sort of divide, at this point, you could divide the theories into 2 kinds. You could divide them into, this is caused by stuff we can't see that can clump up around galaxies. Not exactly the same way as the stars, because if it was exactly the same way as the stars in a galaxy, Zwicky's curve would have been just right. But sort of clumpish. Or it could be something wrong with our theories. It could be something wrong with general relativity or masses or something like that. Now for me, different people will give you different plots. This is the picture that made the day. What you're actually seeing there is called the bullet cluster. Ignore all this. This is just other stuff. What you're really looking at is right here. The expansion of the universe is not perfectly uniform. Everything's not going equally away from everything else. They have what's called proper motion or secular motion. The galaxies can run into each other because they're moving in various different directions. It can happen that they run into each other. Now, if a galaxy consists of a bunch of stars, maybe swirling, maybe not, sitting in a little bubble of other stuff, this stuff that we don't even have a name for yet, I'm eventually going to call it dark matter, but I'll tell you why when we get to that. That stuff is surrounding it like this little bubble. And if it's real, it's really there. If it's just a problem with 1 over r squared, it's not really there. Now that one's moving this way, this one's moving this way, they run into each other. Well, what's going to happen? When galaxies run into each other, they interact. A galaxy is not a very solid thing, but it has enough gas that slows down the gas moving in the other direction. It has enough stars that will gravitationally pull other stars out of their positions or cause gas to swirl, that they interact. They don't go right through each other like that. They hit and they stop and they become turbulent and they become messy. That's what's happened sort of in here. But if there was a cloud of stuff around it that was dark matter, it would continue. It would keep going. And that's what happened. Now we can't see dark matter, but we can see two things. And it turns out in this picture, there's a more recent picture than this, but I couldn't find a good enough image to project. We can see this in two different ways. We can see it in terms of the lensing of the stuff in the background that enables us to, there's a good one there, that enables us to measure the mass of the thing that travels. And something that's not radiating light on its own, has no visible stars in it or anything like that, is very massive and has gone through this. More on that side than on this side, but you didn't expect those two clouds to be the same anyway. They're just two random galaxies that run into each other. More interesting to me, because I think it's more physical, is the blue stuff are X-ray measurements. Hot gas. Galaxies have a lot of hot gas in it. If you look at the average galaxy in X-rays, you'll see it's surrounded by hot gas. Pretty far out. Gravity holds it in, but because it's hot, it's moving fast, it can fly out a long way before it turns around and falls back in. The hot gas is very tenuous and does tend to go through when the collision happens. But it's hot. And if you remove it from, if you take it away from the gravity of its central galaxy, it'll just disperse very quickly. Because it's hot, it's fast. And if gravity's not holding it together, it'll disappear. This hot gas hasn't. It's imaged with X-rays to see where it is, it's that hot, and it's discovered that really it hasn't gotten any bigger than it was based on the mass of the galaxies that were left behind. So there's something that travels. This is not 1 over r squared. This is not messing with radial because it's not up here and it's not down here. It's something that kept going during this collision. So why do we call this stuff dark matter? Well, physicists are really, really good at nouns. Right? We make up new ones all the time. In this case, it's a compound noun, it's dark matter. Why is it called matter? Well, it's behaving like stuff. Right? It's not dark theory problem. It's dark matter. Why is it dark? Well, you can't see it. It's not dark in the sense of opaque. It's not dark in the sense of a black window shade. It's dark in the sense that it's not glowing. And there's a subtle point there, which is, I think, is very important in the physics of what this stuff does. Is, we'll back up a step, and I'm going to ask you a question. Why is a galaxy a flat disk? How did it get flat? Why is our solar system an empty but flat disk? Why don't we have planets going this way and that way? And
Angular momentum?
angular momentum. I told you physicists were good at nouns. Could you put a verb in there somewhere?
Let's see, so conservation.
Conservation of angular momentum. I think that's still a compound noun.
Not quite a physicist yet.
Angular momentum is conserved. That's true. But that doesn't tell me why I don't have a whole bunch of angular momentum of the original big pot. The analogy that you were probably taught is actually slightly deficient. The analogy that you were probably taught was you start with a big bathtub and you open the drain, and as the water goes down the drain, it starts to swirl faster. Right? And there's a swirl that happens. Even the slightest amount of motion one way or the other gets amplified because this mass that's very far out conserves its angular momentum, and as it gets closer and closer to the drain, it has to be turning faster to keep its angular momentum. And somehow there was this big cloud, and it condensed down, and good stuff happened, and that's right. There's more to it than that, because what would be the equivalent in the solar system of a drain? There really isn't any analogy to that. What happens is you start, your galaxy or your solar system or your cluster of galaxies starts as a really big cloud with things that are moving in lots of different directions. And they start to run into each other. And in the process, they dissipate their mechanical energy. But they can't lose their kinetic energy. Excuse me, they can't lose their angular momentum. They can lose kinetic mechanical energy, but they can't lose angular momentum. So eventually, they're going to collapse down into a disk to preserve that angular momentum. And eventually, that disk will start to get smaller and faster as they lose more and more energy. But on average, this big, ugly cloud of things has a little bit, and it's going to preserve it as they run into each other and finally find a disk. That requires collisions. Turning the big lump of ugly gas into a disk requires that they lose some kinetic energy and heat or light or whatever, little screams of pain, while keeping their angular momentum. Dark matter doesn't do that. If I go back to Zwicky's plot and try and work out from the shape of that curve whether the dark matter is in a disk or a sphere, it's pretty much a sphere. It hasn't condensed down into a disk. Well, that actually makes sense, because how do two atoms know that they've come near each other and bounce off each other and collide? If I have two molecules of gas, they're flying through the universe, whether they be bare protons or individual atoms or pure molecules, how do they know to talk to each other and bounce off each other? What do we call that? They collide. That's a verb. They force each other to do something, and which force does that most of the time? It's electromagnetic force. It's the electrons feeling each other as they get too close. Or if they're bare protons, like bare hydrogen protons, it's still the electric force. Well, that's actually quite good, because now we know something about dark matter. We can't see it because it doesn't interact with light. We already know that. But that means it's really not going to interact with itself very much, because that's the same underlying force. That's electromagnetism, the same underlying force. And that's good, because we have evidence that this stuff doesn't really interact. It just sort of hangs out under the spherical influence of gravity. And that's what we mean by dark. It doesn't emit light. Even if you heat it up, even if it runs into each other, it's just immune to light. It's immune to electromagnetism. So dark matter is actually a very nice cartoon for this. It's a nice way of summing up everything we know about this stuff. Seems to be stuff, doesn't do light. Seems to be stuff, doesn't do light. You could throw in, if you want to know a little bit more, gravity. Seems to do gravity. But we don't know whether it does the other two forces. We don't know whether it does the strong force or the weak force. We think probably not, but we don't really know. So now you can look a little bit further. Anybody know what that picture is? That's the beginning of your family tree. That's the farthest back we can see with light, electromagnetic radiation, in the light of the universe. This is actually from WMAP, a satellite, but the Kobe graph is not quite as detailed. It's famous because George Smoot worked on it and got a Nobel Prize for it. People are working very hard to understand the beginning of the universe based on what we can see of the cosmic microwave background. Cosmic in the sense of in the sky, not in terms of, ooh, lab. This is sort of the point. This is looking at how uniform the universe was when stuff started to appear. Basically when hydrogen came out of protons and electrons. And these are tiny differences that you're seeing in the color. Tiny, tiny differences. Here's an interesting point. There's this hierarchy of things now in the universe. There's like meat, and then there's like buildings, and that's sort of a step. And then there's like planets, and then there's like another step to solar systems, suns, and then there's like a step to galaxies, and then there's like a step to clusters of galaxies. In terms of just ratios of sizes, in terms of, you know, sort of what's the biggest shift, what's the biggest step away from a uniform galaxy? Because in cosmology, they used to assume that the universe was absolutely uniform and isotropic, like massively boring. We did cosmology for 80 years before somebody figured out that if we assume the universe is boring, our results are going to be boring. We started focusing on the separation from boring. The first order expansion Taylor series around boring. Where is the biggest step from boring? Is it like from atoms to meat? Or is it like from planets to solar systems? Or what's the thing that most matters when you're talking about the non-uniformity in the galaxy, right? In the universe? I gave it away. It's clusters of galaxies. Planets are just completely irrelevant on the scale of cosmology. And solar systems are really, you know, galaxies just really couldn't care less about individual solar systems. And clusters of galaxies don't really care a whole lot. This non-uniformity is where clusters of galaxies do. There's probably one there, there's probably one there, and there's probably a bunch of there, and there's not any over there. Because absent something like this, there wouldn't have been enough time by now for gravity to take over and make things condense in the galaxies. Now, connecting what this measures, this actual measurement made with a satellite, one can argue whether some of this is real, this might be in our galaxy, but a lot of this is known to be quite good. And the galaxies that we see, you can actually connect all of this data and do a calculation and discover that it doesn't work. With our current theories, you can't take this data plus sky survey data plus knowledge of cross-sections for electrons colliding and forming hydrogen and radioactive decay rates and all this other stuff. You can't put it all together and explain our universe. To make it work, you have to throw in a couple of things. I mean, here are atoms. You're a tiny little part of this, less than a pixel. You have to throw in this dark matter that we were talking about. I'll talk about why it's cold in just a second. And this other thing called dark energy that I'm not going to talk about very much. Like none. But a little bit, 2 sentences. Actually, one of which you're going to provide. Dark energy, what do you think it is? What does it not do with light? Bingo, that's dark. Why is it called energy? Doesn't gravitate. Okay, good. Now, a little bit more work and we'll give you a PhD in dark energy. Because we really don't know much more than that. We know enough to give it a name. We know that it's different from this stuff. And much work is going. Why is this called cold dark? Well, once you start making matter, this funky thing happens, which is you say, you know, matter's got to come in clumps. Sometime in the last couple hundred years, we decided that matter is made out of particles. That wasn't always true. You know, the Greeks had wonderful, long philosophical debates while drinking lots of wine as to whether matter was divisible into atomos or not. And they ended up, incidentally, which side did they come down on in the end? They came down, they did not come down on the side of atoms. They came down on the side of matter is infinitely divisible. Matter is a fluid. There is no basic piece. And it was only with the rise in chemistry about 350 years ago that people finally figured out that atoms are actually real. Here's a wonderful tidbit. It doesn't work as well as it did 12 years ago, but it's still a wonderful tidbit. When did Harvard teach its freshman class that atoms are real? When was the first year that Harvard's freshman physics class had in its syllabus a book that said that atoms are real? Harvard's been around since 1750 something. 1630? 1636 in July.
1930s.
1930s, that's very close. 1927. So not quite, actually it is within living memory still,
So I
but
just think that's when Harvard started.
Oh, 1630? 1636? Oh, much earlier than that. Oh, my mistake. It's surprisingly recent that people figured out that atoms were. Boltzmann, are you aware of the Boltzmann constant K and KT? He committed suicide because he couldn't convince people that atoms were real. So, and then we named a constant after him to make ourselves feel better. But if you divide the dark matter into pieces, you have to decide how small a piece they are. Because if they're small enough pieces, they become relativistic. You can figure out how much energy they have to have just thermally, and if you make them small enough pieces, they become relativistic, and then they can't clump. You have to have, in order to get dark matter to clump around galaxies as much as we've seen, it can't be completely free of interaction. Galaxies in the time they've had have condensed down to be disks. And we know that, most of them have. The ones that haven't have condensed down to be pretty tight little ellipsoids through the electromagnetic interaction. If there was no interaction at all, if there was no way of losing energy at all, dark matter wouldn't clump at all. So there's a game, which some of you may have seen. If you ever go to the fair that shows up in Oakland every summer, they have a great midway. And about half the games on the midway, you can figure out with physics why they are always going to take your money. And one of them is, it's a little track like this. So the track goes up and then goes down and then it goes way up. And they give you a bowling ball and they take your $5. And if you can roll the thing so that it goes over the first one, goes back and forth a few times and stops at the second one, you get this gigantic fluffy rabbit, which my 9-year-old daughter really desperately wanted. And it didn't do any good to explain to her that unless the bowling ball lost energy in this part, it was going to have enough energy to come back out and not win the bunny. That there needed to be, yeah, it was a rabbit thing. There was another, well, we won't go to that story. You have to lose energy to fall into that potential well. Doesn't matter whether it's the bowling ball at the midway or it's a little bit of interaction in dark matter. If the stuff is light enough to be neutrino-like, it's going fast enough that there's no way it can be stopped by the kinds of interactions we know. So what this is really saying is the stuff has to be heavy enough to be cold. That's just an estimate. This is what our galaxy is thought to look like. You live here, more or less. I guess you live somewhere else, but you go to school there. And that's sort of the size of the dark matter halo around our galaxy, back extrapolated by looking out at stars that are far away. This is a computer-generated picture. It's not a real picture, but it gives you the idea that there actually are stars around the thing that we can get good measurements on to sort of measure gravitationally how fast things are going. It's a little bit tricky because we're too close to the center. And what you really want to do is measure how fast they're going this way. But you can't do that. You can only measure the projection toward or away. So it's a tricky calculation, but the cloud of dark matter around us is really, really big. I'm going to skip this one because I'm a little bit behind, but that's sort of an estimate of one around a different, using a different mechanism that suggests that there's sort of swirls around us. I think this is really pushing the data way too far, but with gigantic computers you can do all sorts of stuff. This is actually very interesting. That's a view toward the center of our galaxy. This is dust. The brown stuff in the middle, that's sort of like LA smog in terms of dust. But what you're really seeing here is this oval this is an image made, it's false colored so you can sort of see it with your brain. But you're really looking at gamma rays here. And there's an excess of gamma rays sort of around the center of our galaxy. If you can't measure dark matter because you can't see it in a telescope, you really want some evidence that it exists. And this data is actually now a couple of years old. It's from a satellite by the name of Egret. They measure number of photons per chunk of sky in gamma rays this way. These are their measurements. And this way is energy. Well, what do you do with that? Well, the usual scientific method, I had nothing to do with this measurement, but I find it fascinating. The usual scientific method, you might think that it consists of, say, oh, we have data. You want data? It's yours. You can have it. Good luck. But of course, you want to know what it means. And so what they do is they figure out these are the gamma rays that we expect. We know various kinds of sources in the sky. that we expect will produce gamma rays. They tend to be sort of softer toward low energy. We know roughly how high they are. If you read the paper, they'll talk about it in terms of lots of different kinds of sources, but this is the one that matters the most. And it's just synchrotron radiation from free electrons in the magnetic field of the galaxy. You know that they're out there, you know that they're being bent by the magnetic field of the galaxy, you know they're going to emit some X-rays and gamma rays. These are sort of hard X-rays. Hard gamma rays. X-rays will be over there. And then you're not certain about it. It could, this much could be that much. This is a log plot, so that's a factor of 2. So you know it to within maybe 40%. If nature had come in here or here, we would have said, yeah, we believe it. But it came in up here. And this is the difference. This red. Now, red could mean, ooh, mistake. Or it could mean, ooh, discovery. That's the hard part about doing science. There's no way to look in the back of the book and know whether your difference is a mistake or a discovery. You just have to publish it, and then your audience will say mistake, and some of them will say discovery, and nature, 5 years later, will tell you which it is. The other thing that happens in science is that once you get more data, you can start to look at this more carefully. That first one was the first round of egret data. It was sort of integrated. It's everywhere in the sky. They didn't get a whole lot of data. You can see the error bars were large, so they just added it all up. In the second round of egret data, they actually could look at this excess. Each of these is one of the points like I just showed, looking at different parts of the sky farther and farther from the center of the galaxy. And they can see that, well, there's a little bit of this stuff pretty close in, but as you get farther out, there's more of it. Whatever it is. And it doesn't fall off by like the 1/r of the central bulge. What the hell is it? Well, one theory is it's the decay of dark matter particles. There's a piece of the structure of our theories which goes like this. Space and time are sort of the same. There's a minus sign in there, but that's just details. Space and time are very similar. So any process that can cause two things to come together and later go into different planes, a collision process, if you exchange space and time in that, it looks like a decay process. It looks like something coming apart. They came together for a little while, interacted a little bit, and then flew apart, or there was the one thing in the center that flew apart. It's called ST symmetry. So when you write a quantum field theory, you can't avoid this. Any interaction that will cause two particles to interact can also cause them to decay. And there are factors of pi and 10 and all sorts of other things in the rates, but fundamentally, electromagnetic interaction that causes two particles to exert a force on each other is what can cause an electron and a positron to annihilate to a photon. You can't avoid that. So we know there's a very weak interaction, weak not in the sense of radioactive decay, but weak in the sense of not very big, between these particles because they have to lose a little bit of energy to condense. And therefore, they have to be able to decay very slowly. We don't know whether they decay to gamma rays or they decay to pepperoni pizzas. We don't know anything about that. But you know, you can look for gamma rays, so you do. You find an excess of gamma rays, and you say, oh, that must be the decay of these particles. Really, this slide sums up everything we know experimentally done on the Earth about the properties of dark matter. I love this next slide. We have all of these observations in the sky, but we don't know that those gamma rays come from dark matter or something else. We don't know the particle nature of this stuff at all. We don't know the connection between what happens around our little galaxies and what happened back at the beginning of time. We can claim to have ruled out most things. So here's this egret data that I'm talking about that says there must be something in here. And our high energy physics colleagues, which used to be me, at Fermi Lab and now at the LHC at CERN, will rule out saying, well, there are no particles out here, or there are no particles in here, I can't remember which is which. Doesn't matter. They'll search for particles with various properties, and so far they haven't found any. There's also a problem with the color coding of that. I can't make them out. In my opinion, what we have to do, and I'm finally getting to my experiment, is to look for this stuff directly. So how would you look for the dark matter particles, which, don't forget, are circulating around the galaxy and are moving really fast? You know, not relativistic speeds, not the speed of light, but like much faster than you are. How do you look for them? How would you build an experiment to look for them? You'd get out a magnifying glass and you'd find a place where there's like likely to be one. Well, no, wait, light doesn't work. You're assuming they're particles, but you don't know their mass. You can sort of guess their speed because they're orbiting at about this distance. There might be factors in square root of 2, depending on whether they're in elliptical orbits or circular orbits, but that doesn't really matter. You got it basically right. What do you do? Well, here are your choices. That's our particle. We're going to call it a WIMP, weakly interactive massive particle. Well, massive, we know why it's massive, weakly interacting. We don't know whether it's weak interaction like gravity. We just know that it's not very big. It's sort of, so we're going to hope that it's weak. We think they're particles. We think that they must somehow be able to bounce off nuclei, because they must somehow have some connection, whether it be the traditional strong force, the traditional weak force, or some force we don't know yet, with nuclei, because there's just so much more nuclei than electrons in an atom. We don't know that. We do know that it's pretty much hopeless if they interact with electrons, because in the environment where we work, there are so many photons, so many gamma rays, so many things that interact quite strongly with electrons, that electrons in a target are always getting beat up on by stuff. We just have to get rid of that. We're going to call that a background. So how do you look for this? How do you know that this happened? Now, don't forget, this stuff doesn't happen very often. That's how we haven't noticed it. And if you just take one nucleus and watch it really carefully, you're going to have to wait a really, really long time, like age of the universe long. And your graduate students will get bored long before that. So you need to have a process where you can have a bunch of nuclei that you're somehow watching to detect that this is happening. And this is a slide from Bernard Sedgwick, which I really, really like, that says, we're going to ignore lots of the stuff around the edges, but it says there are really three things you can look for. You can look for scintillation of light, which is when this collision happens, you knock the nucleus out of the middle of the electrons, and the electrons, as they resort themselves, are going to emit light. You can look for ionization. When you knock this nucleus out of the center of the atom, you have separated it from the electrons, and if you put a big enough electric field on it, you'll be able to pull those electrons away and detect them electronically. You can look for heat and phonons. You've dumped some energy into this thing, you've made the solid or the liquid or maybe even the gas vibrate from the mechanical energy of that nucleus. You could look for that. Different experiments will look for different things. Some will look for just one. But looking for one thing is really hard because you want to separate your signal and your background. And in order to separate the signal, which is the dark matter nuclear recoil, from the background of electrons being beat up, it's handy to have two different things. I'll show you why in a second. So my experiment is up in this corner. It uses light and ionization. But there are others. CDMS, which is also a Berkeley experiment, which works with germanium and edelweiss is similar with silicon, works with the electrical signal and heat and phonons. There are a lot of ways to do this, and there are a lot of people trying to do it. You guys don't know who those people are, do you?
Yeah.
There's always a few, so I show it. This is Asterisk and Obelisk. It's actually a French cartoon. It's a bunch of Gauls who tend to beat up on the Romans. And this is the price of using that prior slides that I promised Bernard I would show this one. So this is a typical detector. This is actually a cartoon of my detector. Oh, the movie is actually working. Excellent. This is a xenon molecule, and here comes the WIMP, and it knocks that molecule. And it liberates a few electrons that are drifted upwards to here, and it made a flash of light. And when the electrons get to the top, as they exit the liquid, they also generate a flash of light. And those two flashes are imaged by phototubes at the top of the funnel. So the detector works by seeing light. It sees a little bit of light when and if a WIMP, or a neutron, which can do the same thing, hits an atom somewhere in this big tank of liquid xenon. It's about this big, 350 kilograms. Liquid xenon is so dense that aluminum floats in it. And stainless steel almost floats, but aluminum floats. So if you drop a chunk of aluminum, it bobs to the surface. You can't actually do that because it's also in minus 100 degrees C, but it would be nice to be able to try. And also you can't, even though you could, it's not even nearly as cold as liquid nitrogen. So you could have a dewar full of liquid xenon, but you don't, because liquid xenon is about $3,000 a kilogram. So you don't want it evaporating into the atmosphere. Also, it's like nitrous oxide. It makes you silly, really silly, particularly when it's $1,000, a couple $1,000 a kilogram. This is how we separate that background, which is electrons, from the signal we're looking for. This is actually data that was taken with neutrons instead of dark matter particles. We don't have enough dark matter particles to do this, but we have lots of neutrons. What you've got here is how much energy is absorbed in the detector. It's basically how much light. And here is a funny, it's a log because otherwise you wouldn't be able to plot it on a curve as it goes up. But it's basically the ratio of the light you see in the first flash from the actual collision and the light you see in the second flash, which is called S2, at the top. And basically, when an electron gets hit hard, only one electron gets moved, and then it sort of rattles around. When the nucleus gets hit hard, all of the 100 and some odd electrons of the xenon are disturbed. So you get a different charge to light ratio. And you can, out here where there's a lot of energy, you can separate. Now we don't know how much energy we're going to get. We don't know how much recoil there will be from this dark matter particle, because we don't know whether it's more massive or less massive than xenon. If it's sort of truck-like compared to a Volkswagen xenon, it's really going to transfer a lot of energy. If it's sort of tennis ball-like compared to a Volkswagen, it won't transfer very much at all. So we don't really know where on here we're going to be working. There are a lot of people who suggest it. Now, the biggest problem with experiments is they're never as simple as you want them to be. What do we need for this experiment? Well, we need some xenon. Oh, shoot, it needs to be liquid. It's got to be cold. And it needs to be watched by phototubes. And it actually needs to be pressurized so it doesn't boil away. And it needs to be shielded so we don't have much radioactivity. And it's starting to get really, really complicated. This is sort of a computer-aided design, mechanical engineer sketch of the first phase. The xenon volume has to have stuff at the top and bottom to support it. It actually has to live in a cryostat to be cold. That whole thing needs to live in a tank of water to protect it from radioactive decay coming in, not because it would damage it, but because just the radioactivity of the potassium in your bones is enough to be visible in this detector. So you can't do that. We can win a little bit, and this is why I mentioned that xenon was so dense. Xenon itself can be made very, very pure. It's a noble gas. It has no nasty isotopes. We can refine it very pure. And the outer 10 or 15 centimeters of it sort of shields the inner part. It acts like a not radioactive shield around the inner part. But it's thousands of dollars per kilogram. And a kilogram of liquid xenon is about that big. So it's a very expensive shield, and you'd much rather have it be shielded by something cheap like water. This is the actual device being assembled. You can see it's made out of ultra pure copper, so it's really cool looking. These all have to be done in clean rooms because physicists aren't very clean. And dust, and particularly radon in the air, is just really bad for this detector. This is the clean room here where it's being assembled. This is an undergraduate, Adeline, who works here, making a piece of electronics that would go into the thing. These are some other Berkeley pieces. This is me. I'm my graduate student. She's got her suit on upside down. These are separate. That's in the clean room. One of the things about working in clean rooms attract something. There are always people taking pictures of the clean room. It's just really amazing. But the detector's been built. This is it now. You can get some idea of the scale for it. These are pictures of it being assembled and dropped down into a water tank on the surface. What do I mean by on the surface? Well, here it is. The water tank's about to be filled. We ran the thing over the summer. It's now back out and being prepared. Where it was in a water tank. This is on the side of a hill. So this is sort of ground level dropping down. And this is this water tank that was cut into the side of the hill. But where it's going is here. What do you think that is? What do you think you're looking at? It's a big room. It's easy to be a big room with one person. This guy's name is Kevin Lesko. He's about 2 inches taller than I am. Yeah, inch and a half taller than I am. I'm not going to give him the full 2 inches. Doesn't it look like it's like carved out of rock?
Yeah.
So it's like, maybe, wait a second, the roof is made out of rock. This is 4,850 feet underground. Where his feet are 4,850 feet underground in the Homestake Mine in South Dakota. This is an expanded version. You can see some of the original walls here, and you can't really see it, but it's over here, of this cavern. That's Ray Davies. He filled this tank in that same cavern with cleaning fluid. We don't use this stuff anymore, but it's called trichloroethane. It's got a lot of chlorine in it. It's not chlorine gas, because chlorine gas is a gas. It's the sort of the densest liquid you can make with chlorine easily. Tremendous carcinogen. I'll come back to that in a second. And he used it to detect the neutrinos from the sun. So this finishes my story from the beginning, right? This is how we know that the sun burns with fusion experimentally, which is that Ray Davies, who won a Nobel Prize for this work, was able to detect the neutrinos from that fusion in this tank, which is in the Davis mine. This tank was eventually, for a later experiment, put inside of a water shield. That's Ray swimming in the water shield at Berkeley. You get a parking space for a Nobel Prize. At Homestake, you get a swimming pool. I tend to refer to this as hard hat science. This is some of my collaborators eating lunch underground in the mine. Because if you think about it for a second, you're 4,850 feet below the surface. Do you walk up the stairs to go get lunch? Do you even wait for the elevator to go get it? It's an 11-minute elevator ride from down there to the surface. Because it's a really long way. And I can show you the pictures if you're interested after. The cable is a very interesting piece of technology. There's a cable that lifts you up and down, 7,000 feet if you go the whole distance, although the bottom is full of water right now. And I thought for a long time, when I first said, would you like to go down below, there's the cable. That's a really long way to fall. This is the top of the mine, right there. This is what the Black Hills of South Dakota look like. It's a beautiful part of the world. It's full of very, I don't even want to use the word friendly, I want to use the word accomplished and focused people. But when we needed to get a piece of, we were trying to get a piece of equipment around a corner into a cavern, and it was really hard and it was really stuck. And Mia called me up there, I still have phones down there. Mia called me up and said, this is really, really bad, we're going to have to disassemble that. By the time I had figured out that another approach, they had used explosives to get the piece of rock out of the way. It's a very can-do attitude. This is the old mining complex, because when you get, it's a gold mine. It's no longer used as a gold mine. But when you get gold out of the ground, it's actually very hard to get the gold out of the rock if you just got it out of the ground. It's a very small part of it. And this is all of the technology that was done to do that. That building right there with the chimney is where our detector is being assembled, but eventually it's going to be 4,850 feet down that way.
Is the mine that deep?
The mine goes to 72.5, 7,205.
Mine is what?
The mine is 7,000 feet deep at its deepest point. I want to show you another thing. This is actually in Rapid City, which is nearby. This is the South Dakota School of Mines football team. It's not a great picture because I got it off the web. People in the background. See the cars at the top? We have Memorial Stadium. You guys been to football games? If not, you should go. It gets so bad here that the home team gets to watch the game from their cars. Because it's too cold to watch it from the stands, and the visitors have to watch from the stands. It's a drive-in football stadium. Eventually there will be a large underground laboratory underneath this mountain. We're going to be in part of it now. There are 2 hoists that lift things up. They're planning to do all sorts of interesting stuff there. This is the collaboration. This is the size of the group. We're 11 institutions. I have no idea where I am in this, but Mia is right there. I'm probably not even in And now here's the bad news. There are a whole bunch of experiments that are trying to find WIMPs, but we don't know what their mass is. They could have any mass sort of anywhere. They can go that way a little bit and this way a little bit, but they're astrophysical arguments that they can't be much lighter on this side and they can't be much heavier on that side. Actually, the arguments here are just, if they're much heavier than that, there aren't enough of them that we'll be able to see them, because each one takes up a huge chunk of the stuff. They have the mass of a baseball. Only one will come through every couple of thousand years. We're just not going to see it. On this axis is what's cross-section, how probable they are of interacting with an atom that they go by. And we really don't know that. We know that it's not zero, but we don't know how big it is, and we want to measure it. And of course, it's easier to detect ones up there than it is down here. So as people build these experiments, they sort of push down. And those solid lines have all been done. Lux, by the end of this year, will be down here. And others, CDMS, which is the experiment I mentioned earlier in 2013, hopes to push down to here. There's going to be a continuous effort to push all the way down. Notice Lux 2009. 2009. I'm pretty sure we've done that. This experiment, the Lux experiment, was originally supposed to have gotten to here in 2009. This is an old slide. In fact, our schedule looks like this. We've been building and running it on the surface. This year we're going to move it underground. We really promised results within a year, and then we start building the next one. These experiments take sort of traditionally 6 or 7 years. We're trying to speed this up to about 3 or 4. It's really hard. It's like really, really hard. We keep making mistakes. Our surface run in that water tank on the surface was a screaming success, except for the fact that we had a piece of plumbing break inside the detector and we couldn't get the xenon back out. And we had, rather than pump it back out, we had to heat the thing up and boil it and drive it back out. Which was good because how much does xenon cost? Right, a couple $1,000 a kilogram. We have 350 kilograms of it and we wanted to salvage and reuse it again. So they're technologically very difficult objects. They're not just, oh, start with a sphere of xenon, make it the most boring place in the universe and then watch it carefully. Pretty close to that, actually. But that's what we do. The whole purpose of this is to be able to answer the question, how do you know that you have the appropriate explanation for what Zwicky figured out when he was trying to figure out, how do you know that those are actually swirling constellations, or swirling collections of stars? And so now, 65, 66 years later, we are still working on that basic question. That's it. Thank you very much. Anybody have any questions? Does somebody know how to turn on the lights? Oh, we'll go back to this. Yeah.
So, sorry. You mentioned briefly that Ray Davis discovered neutrinos from the sun, kind of proving nuclear interactions. But even more important was that he discovered the neutrinos that didn't discover, the missing neutrinos.
Yeah, the story is, I'm old enough to actually remember this story. The story is that Ray Davies did not discover the neutrinos from the sun. He discovered a third of the neutrinos from the sun. A better example of the phenomenon is Bill Fairbank at Stanford. Bill Fairbank at Stanford was looking for magnetic monopoles. And there actually are theories that say there could be a particle that has the magnetic properties of a monopole. When you study electromagnetism, if you haven't already, you'll discover that in the real world there aren't any of these, but you could have a particle that really does this. In Maxwell's equations, there's a zero that could be something else. Bill Fairbank built a detector for these, hoping to find one zipping through from cosmic rays or something. What's the worst possible outcome when you do that experiment? Finding a lot, that's cool, right? You found them. Finding none, that's cool. You can set a limit. What's the worst possible outcome? Find one. Right? Because it's very hard to know whether it's a mistake. It's very hard to know what you conclude from a limit, and you're tempted to spend the rest of your career running this detector in various different ways. So if the gods are going to curse you, they're going to give you one of what you're looking for. So Ray Davies found a third of the neutrinos from the sun that were predicted. Well, what could that be? It's an incredibly tough experiment. He was looking for individual, like 6 or 7 atoms of germanium that had been made out of chlorine in that big tank a year. And he found like 2 or 3 instead of 6 or 7. What would be your first guess? He lost the rest of them, right? They didn't get successfully swept out. They weren't properly counted. There's something in the device that absorbs them. He spent decades convincing the world that he could measure these. Literally decades. And after 22 years, a small industry of doing other experiments using other atoms came up, and it turns out his number was right, and had been right from the very beginning. He was just such a thorough guy. So in addition to proving that the sun burns on neutrinos, he also proved that neutrinos have very interesting and unexpected properties. They mix. That's another talk. You had a question.
Yeah, so you mentioned earlier that they're sort of saying, well, we can see the gamma decay from, the gamma rays from decaying dark matter. But you had just previously said that dark matter doesn't couple to light.
But its decay products might.
So it would decay into, say, like pions, and the
Or
pions.
decay into 2 charged particles, one of which emits gamma rays. So for example, a neutron, which is immune to the electrical force, decays into an electron and a proton, both of which are not immune to the electrical force.
So the thing that that the dark matter would couple then hopefully to the nucleus via strong or weak.
So there's a weak coupling means 3 different things in modern physics. There's something called isospin coupling, which has to do with what kind of quark you are, or whether you're an electron or a neutrino. And this is called the weak force of radioactivity, the weak force that generates beta decays in radioactivity. But what we really know is that it's weak in terms of the number is like that number. We don't necessarily know that it's coupled the same way. We know that it's not coupled via the strong force. The strong force is what holds protons together, and the van der Waals equivalent of that is what holds the nucleus together. We know that that's not true for dark matter because the condensation would be too fast, but it could be something like that that only couples to quarks, and we call that strong. We're very good at putting labels on things, right? They gave us a dynamo label maker, and we've been labeling reality for the last 100 years. I should show you the picture. I have it in my laptop. There's the safety in a mine is a really big thing, and you really take mine safety lectures seriously when they're given to you by somebody with 6 fingers, right? It's a very dangerous part of the world. And one of the things, whenever we send tool chests down below, everything is inventory. It's almost like surgery. And not one of my graduate students, but a Case Western graduate student, labeled one of these tool chests. Things for sticking, things for turning, things for cutting, things we hope are not radioactive, things we hope are radioactive, etc. Just labeled all of these and got in so much trouble from the safety people who have no sense of humor. I mean, it's probably one of the most dangerous environments on the planet. And we're trying to do science in it with people who have a hard time taking rules seriously. It's an interesting problem. This is by definition have a hard time taking. Our whole purpose in life is to try and prove rules wrong. Okay, if you're trying to prove Newton's laws, maybe that's not such a good idea. If you're trying to disprove somebody's theory about dark matter, that's a career maker. If you're trying to prove that you really can breathe carbon monoxide, other questions? Any other questions? No other questions. I can't believe that the talk was that clear. That's just not true.
So you had sample data of putting neutrons into your experiment. How did you get the neutrons in?
With smoke detectors. It's true. So how does a smoke detector work? Very well, thank you. No, but seriously, how does a smoke detector work? The little beeping obnoxious thing, how do they work?
Radioactive decay of, I think, it's not cesium.
Americium. Americium. The way that it actually works is that it's an ionizing decay that if there's smoke in the air, the smoke will attract the ions and become electrically charged. And just like an electrostatic air separator works really well at charging the dust in the air and then pulling it out electrically. It's just like that, except it's a little tiny one that goes off if it gets any dust out of the air. But that particular isotope also emits neutrons. It emits all sorts of stuff. It emits alphas and neutrons and gammas. The gammas are what it cares about. The gammas and the alphas are what they care about for making it work, but it also emits neutrons. So if you can get a chunk of that stuff, you get neutrons. And so we have radioactive sources. We have cesium that we run up and down that makes. One of the things that I didn't talk about that's actually very hard is you need to be able to drift these individual electrons that far without them being absorbed into a molecule. Right? You know, now you got to learn about chemistry. It's a noble gas, so you think of it as a little ball with all of its electrons tied up, and it's just sort of there. It's not going to do anything. But there are all sorts of interesting chemical things that can happen, particularly if you have impurities. So if you have CO2 or water or anything else, even a few parts per million, they will pick up these electrons and become negative ions. They're very happy to do that, and then they don't keep going. They stop. So the xenon has to be extremely pure. And one way to measure the purity is to generate light with gamma rays up and down the outside and see what fraction of that charge gets to the top. So we use lots of different kinds of radioactive sources for that. Underground, we don't have approval to take the sources underground. Well, that's going to be a problem. Alice?
So how do you differentiate between the neutron excitations or whatever?
You don't.
You don't?
You have to keep the neutrons out.
Or sorry, the neutrino? You mentioned something about another one that hits it. Is that like the only way to make sure it's
So
not around?
neutrinos, the neutrinos from the sun are not a problem because they're low enough energy. Neutrinos, so a cosmic ray hits the top of the atmosphere, blows up a nucleus, generates a lot of pions, they decay, make muons, and you get sort of a cluster of charged particles, which is the cosmic ray shower, and a whole bunch of neutrinos from that process. Those are what were used to determine the muon neutrinos mix by the chemioconduits. And so we have a really good estimate of their flux, their higher energy. And they will be visible in our detector. They form what's in a future generation detector. They form what's called an irreducible background, a certain number of events. But we can calculate that really precisely, within like 50%, which is considered really precisely. We know that number, so we just subtract those off. The biggest problem is not photons. We can get rid of gamma rays from radioactivity using processes I described. But if we accidentally build a neutron producer like radon into our detector, it will look just like the signal, and that will be bad. So we just can't do that. So you do it in the clean room, and you assay it and measure it. So here's a question for you. You guys, how many of you are not from California? A few. Do any of you know about radon in basements? You've heard about radon in basements? Radon has a 2.5-day half-life. How can you get radon in basements? In fact, why is there any radon on the planet at all? The planet is significantly older than 2.5 days.
You got uranium.
Say that again?
You got uranium with a very long half-life that's producing radon.
No, close, but not quite. So there's this long decay chain that starts with uranium and goes through 6 other things before it gets to radon. So why is radon the problem? Why is radon the thing we're worried about? As opposed to the things that are above it or below it, like polonium and radium and hafnium and unobtainium and all these other things. Why? Because it's a gas. And all the other things are part of the solid and they sit there in the rock, and the radon, which is a noble gas, can come out. The perfect thing to make one of these detectors out of, you want heavier atoms because you really want them to be big targets. Noble gases are good because of this electron drift problem. The perfect thing would be to make it out of radon. Unfortunately, it's radioactive. Fiercely radioactive. And after 2.5 days, half of it would be gone. And that would be embarrassing for the funding agency. Xenon is the second best. As you get to the lighter ones like krypton, krypton it turns out is radioactive too. Argon, a little bit radioactive, but you can probably make it work. Helium is great, but to get a lot of mass for it, A, you've got to have it be really cryogenic, really cold, and B, you need a lot of mass of it. So we go with xenon. We go with what we got. What we really need is a heavier nucleus that's stable. So if any of you happen to have any of those, you know where to find me.
The W and wind, you mentioned there's 3 kinds of weak. The W and wind, I take it, is not the weak force.
It's a euphemism. We don't know what it is.
But you don't mean it univocally to be the weak force.
No, I mean I don't know. It could be. Could not be.
So
I
it's
don't
about
know.
the same scale? Is that why they
We think it's roughly the same magnitude, but we don't know it's the same magnitude.
Okay, but the theory doesn't base on the
Theory doesn't
fact-
tell us jack. I mean, there is no theory for what this is. Well, I mean, so what's, 0 or a lot is the number of events you want to find. 1 is the number of theories you want to have. And depending on who you talk to up on the fourth floor, the right answer for theories right now is either 0 or a lot. Right? That's not what you want.
Can you really briefly explain the difference between a WIMP and an axion?
Axion is a detergent. The story there is that there is a particle named axion. It was the product of a bet. Can I make that go up? Does anybody know how to make that go up?
There's a control next to you.
There are 3 famous bets in high energy physics. And the one that's easiest to explain is called penguins. They're in high energy physics, you guys, I know the world, if you want to leave, go ahead and leave. Well, I'm not offended, it happens all the time, I've got kids. In high energy physics, we make diagrams like this that are called Feynman diagrams. And that's the traditional one. In the United States, they're drawn with time going, I can never remember, going this way, and in Europe, they're drawn with time going that way, but it doesn't really matter. It's the idea that 2 particles come together and become a 3rd particle that falls apart into 2, something like that. You can trace the constituents as they move around. And Ed Turner bet somebody that he could get any word the person wanted into a scientific paper. And the answer was penguin. And so he wrote a paper about diagrams that look like this. They called that a penguin. And now there's an entire industry in penguin diagrams. If you go to the High Energy Physics Paper Archive and you search for penguin diagrams, there will be tens of thousands of papers. Does it look like a penguin to you? No. And particularly because the way that they're actually drawn these days looks like that. And that really doesn't look like a penguin. Axion is exactly the same way. I can't remember her name. She was in SLAT when I was there as a graduate student. I can picture her. Quinn. Professor Quinn, because I was a graduate student, I'm going to call her professor till the day I die, bet somebody the same kind of bet and was given the task of axion, which is the name of a laundry detergent at the time. And so she wrote a paper about a particle that solves something called the strong CP problem. Now I have to admit, I actually worked on CP violation for 11 years, and I do not understand the theory behind axions. I spent an entire summer trying to teach myself the theory behind axions, and I can't. And I suspect that it's actually an in-joke. But it's got to be more than that, because people are looking for it. An axion is a class of particle never observed that is sort of the ghost twin of the photon. Photons carry angular momentum. They're what's called vector particles, which means that if you look at them in a mirror, they're not really carrying angular momentum. It's a subtle and tricky thing, because angular momentum is an axial vector. If you look at angular momentum this way in the mirror, it gets flipped in a way that a regular vector doesn't. And we can talk about the minus signs, and we can talk about whether mirrors are actually the right example, because mirrors are not actually p-symmetry, but it's close. It's the same basic idea. There's this thing called a vector, and they call that axial vector. If you go into my branch of physics, you'll spend a lot of time wishing they had named them something different. It's like, the universe could have had a left-handed rule. Any of you left-handed? You know the advantage of being left-handed in electromagnetism? There's 3 right-handed rules, actually 4 if you count properly, but there are no magnetic monopoles, in electricity and magnetism. And you have to get that right-handed rule to know how the forces go with the currents and stuff like that. And you're going to be doing this in the exams. And everybody else is going to be doing this in the exam, and they're going to get it wrong. Think about it. This is not your right hand. But we could have used left hands. If we'd been smart enough to do that, we could have really stuck it to you lefties even more. My wife is left-handed. She points this out to me all the time. So there is a problem deep. What's stated is there is a problem deep in the core of the modern standard model that has to do with this thing called the strong CP problem, and it has to do with why it is that we're experimentally quite certain that nuclei preserve this thing called CP symmetry, even though neutrinos don't, and they shouldn't. Photons should, because of this axial vector thing, cause them to not, and they don't. And the only way anybody's been able to explain it other than saying they just don't get over it is the Pesci-Quinn theory, which predicts that there are very light photon-like particles that are axiomeric, called axions. And people have looked very hard for it. If you have axions interact like this, if I want to draw diagrams, here's a photon, I am a photon, I'm moving along, and I can emit an axion and rejoin, and it adds a tiny amount of effective mass. It slows the photon down a little bit, makes it act like it's not quite moving at the speed of light. We're pretty sure that photons move at the speed of light, so there must be some reason that this doesn't happen. So in that case, you have to break this. You have to invoke this symmetry and say two photons can interact, form an axion, which for some reason can then become two other photons. That's my axion. They're usually drawn as dashed lines. So the way you look for this is you start with, you turn this around, and you say axions coming from like the sun or somewhere where there's a lot of chromodynamics going on, bounce off a photon in a magnetic field and make a new photon that you can detect as microwaves. And Livermore has a big experiment that's reusing an old magnet to do this. Nobody's found one yet. Quinn, who's a very nice, Helen Quinn, who's a very nice person, absolutely deadpan, will make predictions to 4 significant digits about the properties of the axion. And you'll rule that out, and she'll make another one. And you'll rule it, and you just wonder whether it's just an elaborate practical joke. Because we don't know, right? It's a theory you can write, it's mathematically consistent, it explains a mystery, but you can't find the damn thing. Other questions? Hydrogen physics really does have a sense of humor. It really does. Because you have to have a sense of humor. It'll drive you crazy if you don't.
Yes, wasn't there a quote from Holly Cloakroom yesterday? I've done a horrible thing. I've gone and predicted a particle that can't be detected.
Yeah, except he was wrong, right? It could be detected, but he didn't know that at the time. Any other questions? I'll hang around if you want to see pictures and stuff. Thank you all.
Thank you so much, Professor Jacobsen. That was a great lecture, I must say. I also think it definitely shed some light on a really dark piece of physics.
We should all come back March 13th is the next conference.